Okay, so this is just a review of power series, and we have our first definition. A power series about x equals a, that's the center, is an infinite sum of the form below. And you can also, as I mentioned, write it as an infinite series. So what does this look like? So here's an example of a power series, and this is centered about x equals 2. So our definition for the interval of convergence. So the interval of convergence of a power series is the set of x's for which the series converges. So just a couple notes here. So this converges to L if and only if so it converges to L if and only if its sequence of partial sums converges to L, i.e., in other words, the limit as n goes to infinity of Sn of x is equal to the limit as n goes to infinity, different n, Sn of x. So basically, the limit of the partial sums, this is the partial sum, so the limit of the partial sums, it's basically just goes to infinity, is equal to the infinite sum. So or my note 2. Okay, so for every power series that has an interval of convergence, if it only converges at 0, it's not to 0, it's at 0, then we say the radius of convergence is 0. R is equal to the radius. So if we have x minus a, so that's centered around a, less than r, again, the radius of convergence is r. And lastly, if r is infinity, then it converges everywhere. So one of the tests that we can use to find the radius of convergence is the ratio test. It's actually the absolute ratio test. So if the limit of the n plus 1 term divided by the nth term is equal to p, the absolute value of, then if p is less than 1, it converges. If p is greater than 1, it diverges. And if p is equal to 1, it's inconclusive.
So first example.
So let's find the interval of convergence of this series. So we're going to take the limit of a to the n plus 1 all over a to the n, the absolute value of it. Okay, so we can just flip and multiply that. In the future, just skip that step anyways. And let's rearrange. We can distribute that limit. Oh, and these have the same base, so we can subtract those exponents. If we want, we can multiply by 1 over n. If you can't see that this answer is 1, let's multiply by 1 over n. And this, since there's no n there to plug it in, it's independent of that n, so it's x minus 2. And we can see as n goes infinity, we get 1. This becomes 1. This is equal to x minus 2. So remember, if x minus 2 is less than 1, we can find our radius of convergence. Well, my radius looks like it's 1. We can find the interval of convergence. There's my interval of convergence, but we must check the endpoints. So those are the values of x that this series converges for. So we have to check 1 and 3 to see if it converges at those values. So let's plug it in for 1. So the series is this, and basically we replace x with 1. So this looks like it's the harmonic series, which by itself does diverge, but since it's alternating, we apply the alternating series test. And this is our famous one that it does converge. So it converges using that alternating series test. And if you remember, it's because it's decreasing, alternating, of 1 over n does equal to 0. So those are the 3 things that we have for the alternating series. So it converges. Now let's test the x equals 3. So it's going to be 3 minus 2. So this is, so we don't need 1 to the n. That is just 1 over n, which diverges. It's the harmonic series. So my interval of convergence is including 1 up to 3, but not including it. And our r was 1. Let's do another example. Okay, so let's do the same thing. We're going to find the interval of convergence for this series. So we're taking the limit a to the n plus 1 all over a to the n, the absolute value of it. And so we're going to simplify it. So we can pull out an n plus 1, and that's times n factorial. It's still the absolute value of, so we can see those will cancel. So this looks like it's going to be the absolute value of x, and that clearly is going to be times infinity. I don't care what x is going to go to infinity, which is never going to be less than p. Again, that's our p. If p is less than 1, it converges, but it doesn't. But since p is equal to infinity, it diverges, except at the center, x equals 0. So if you want to look at it as an interval, it's just from 0 to 0. Again, if you look at, just so you can see what I'm saying, if I plug in x equals 0 here, it's x equals 0 plus 0 plus 0 plus 0, you get 0 for every single term. So of course it's going to converge at 0 at the center. That's the center. Let's do another one. Okay, so same thing. P is basically the limit is n goes to infinity, a to the n plus 1. Plug it in. Flip and multiply. Rearrange. And I don't really actually even need these because it is positive. This one we need it. And we pull out that, and then it's times n factorial, which will cancel with that, the 1 on top. Looks like just plain old x there. So this is absolute value of x, because there's no n to plug in. So this goes to 0. So it's 0 times x, which is 0. 0 is less than 1. When? For what values of x? So basically, always. For all values of x. Therefore, it converges everywhere. So my interval of convergence is minus infinity to infinity. Or if we asked for the radius of convergence, is infinity.